Hi, I'm with Team 21021, and we're excited to present our real-time instrumentation characterization kit sponsored by Roche.
Hello, my name is Miguel. Our team works with Roche Tissue Diagnostics, a producer of cutting-edge tissue staining systems that are used in labs around the world. The staining system adds and controls volumes of reagents at microliter scale during staining, which can last hours. The amount of fluid on the slide is one of the most critical parameters for their system staining quality and one of the hardest to measure. Currently, Roche can only determine the volume of the fluid at a point in time on the system by physically wiping the fluid from the slide and weighing it, a time-consuming and error-prone process. Time domain volume information will give Roche an unprecedented insight into their most critical processes. The purpose of our project was to design a proof of concept for a system that reports the volume of the fluid on the glass slide over time without interfering with the staining process. So we interviewed Roche project sponsors to understand the current issues by identifying the core functional requirements, which are a resolution of 100 microliters, a range that goes from 0 to 2 milliliters, accuracy within 10%, and a response time of 10 seconds.
Hi, I'm Haibei. Our project was based on selecting a core technology that can meet the challenging requirements of Roche's particular needs. Our project's early focus was carefully analyzing and determining the core technology that will meet these unique needs. This was the focus of our first field sprint. We then chose the core technology for our system by objectively scoring and weighing the radically different technologies we had identified. These include a detailed analysis of each of the options. Ultimately, our selection was driven by the unique requirements of the design. Our trade analysis leads us to select a deceptively simple design, sensing fluid on the slide surface by looking at how it interacted with the electric field from sensing pads on the system. This is similar to how capacitive touch system things where your fingers are on your phone's touch screen. However, we need to push the technology further. We completed detailed e-field simulation in QuickField to test the theory. This detailed simulation showed us that our design was feasible. The next step was to de-risk our project by validating our simulated result. Our validation showed that our simulation was very accurate. Our predicted response slope was within 2% of our measured response slope.
Hi, I'm Mark. To create our final design, we leveraged the knowledge we gained from our simulations and testing, corroborated by back-the-hand calculations to create a basic design. However, there is uncertainty in various parameters of our design, so we varied both our critical design parameters across a range of values in 5 steps for a total of 25 different designs. We developed a design of experiments to choose the best configuration without needing to test them all. We first tested a few samples at the extremes, then at the center of our design spread to estimate the variation over the design space, then iterated our testing to find the configuration that was globally optimal.
Hello, I'm Wei. Our system consists of the GUI Capacitance to Volume module, AD73046 driver, Pinhole Lova library, and the Rig V3 demonstrator. Our system is written in Python 3. The GUI displays the volume measure result of the solution up on the screen, and it fetches the data from the capacitance to volume module. Our capacitance to volume module is what converts the capacitance volume that is obtained from the AD73046 driver using a polynomial fit based on collected collaboration data. The AD73046 controls the communication with the Rig V3 demonstrator through the Pinhole Lova adapter. In order for the system to function properly, the AD73046 driver sets the capacitance to digital converters function of registers to their proper volumes. The Pinhole Lova host adapter communicates to the Rig V3 demonstrator via I2C protocol. The Rig V3 consists of 3 parts: our capacitance to digital converter, AD73046 volume sensing pads, and the glass glued to the device. Overall, our system starts by waiting for a capacitance reading from the AD73046 driver. Once it receives the data, The capacitance to volume module will do the conversion and output the result volume to our GUI. The GUI will then display it up on the screen.
Hello, my name is Duncan. As for our delivered product, we have nicely packaged the device all together in one neat PCB. We have included a Binho Nova as a communication device between our PCB and the host computer. As you can see here, the PCB has a sensing glass already applied and glued down to the device we are connecting to. All I need to do now is connect the PCB to the Binho Nova, then connect the Binho Nova to the host PC. The GUI is provided as part of our delivered product. Now, with our device connected, we can power up the GUI and connect to the Binho Nova through the COM ports. You can either take single samples or let the computer automatically take samples for you. As you can see, the GUI will show a response and measure the volume applied live. As the program currently stands, it will support future work by making calibration curves modular and easy to select. The program uses a CSV input file and makes adding and editing curves a breeze for follow-up work.
Hello, my name is Alexis. We verified the system over 3 phases as we improved performance and added system functionality. We verified by inspection and test, and tested the system's resolution, range, accuracy, and response time, our key performance requirements. Once testing was done, we analyzed the output file to determine the system's performance. All requirements passed except for accuracy, and since accuracy is a condition of the response time requirement, that requirement fails as well. As seen in the SRVM, we exceed the resolution and range requirements with high margin and meet all other requirements except for accuracy and response time. Hardware deliverables include 10 evaluation units and drawing documentation, and software deliverables include the source code and fluid characterization documentation.
Our system did not meet our requirements for accuracy. We believe this is primarily due to the mechanic variability in our system. Gluing down the glass was a hit, and this process introduced significant variability, not just between runs, but between PCBs. Our team did not have the mechanic design expertise to address these challenges. The bulk of future work will be in driving down repeatability issues caused by inconsistent gluing, coverage, placement, and uniformity, with improved gluing processes and gluing jigs.
Thank you for joining us today. We want to give a special thank you to Roche for the project, and a special thanks to Marcus Engineering for letting us use their lab space. And we want to give a big thank you to Jessica Owens and the Roche team, along with Kat Merrill from the U of A, for helping us with our project.